Day 10 will look at something called shifted geometric sequences and limits. For the warm-up, we'll take a look at what we've been looking at in the past part of the unit. So the first part is I give you a sequence. Can you tell me, is it arithmetic or geometric? If it's arithmetic, find the common difference. If it's geometric, find the common ratio. And then can you write the recursive formula? We'll also take a look at the explicit formula. So if you take a look at the first one, it alternates from negative to positive, and that means it has to be geometric. It's the only way you can get from a negative sign to a positive and a negative to a positive. So if it's geometric, it has a common ratio, and to find the common ratio, you just take any number and divide by the one before it to get the common ratio. So here the common ratio is 2, negative 2, and what that means is if we multiply any number in the sequence by negative 2, we'll get the next term in the list. So let's write the recursion. The first term, so you have to identify the first term so we have the same list of numbers, is negative 6. To find any term, you take the term before it and you multiply by negative 2. So you can write it like this. You can put the negative 2 in front of the a sub n minus 1, but that's the recursive formula. We can write the explicit formula as well. Explicit is, it's going to be exponential, right? So we need a starting value. And there's two ways to write it. I like to start at the 0 term, so I'm going to go backwards one. Instead of multiplying by negative 2, let's divide by negative 2 to find the 0 term. And so negative 6 divided by negative 2 would be 3. So we're going to say our starting value is 3. And we're multiplying it by negative 2 every time. So there is the explicit formula. If you want to start with the first term, you can say to find any term, we'll start at negative 6, the first term, and then we'll multiply by negative 2, but then to the n minus 1 power to shift it to the left one. So there's a review of what we've done for the past few weeks. Let's take a look at the next one. The next one, I'm going to guess is arithmetic. So to find the common difference, you just take any number and subtract the one before it. So if I take 7.23, and I just have my calculator right here, and subtract 7.11, I get a common difference of 0.12. I'm just going to test it a few more times to see if it's true for all the terms. So I do 7.35 minus 7.23, I get 0.12 again, and 7.47 divided by 7.35, I get 0.12 again. So here's a common difference, and that common difference is we're adding 0.12 every time. So then the recursive formula, again, we need a first term, so we have the same list of numbers. And then we say to find any term in the sequence, a sub n, we take the term before it and we add 0.12, which is the slope. So if you want the explicit formula, we say to find any term, the slope is 0.12. So we multiply that by every term. And then we have to figure out what the starting value is, the y-intercept, so we'll subtract 0.12. And if we do that, we get 6.99. So our y-intercept would be 6.99. We start there, and we're adding 0.12 every time. So there's the explicit formula. All right, so let's take a look at one more problem using the explicit formula. It says the value of your car depreciates as you get older. This is actually an example of something we did last unit. Suppose your car loses 2/5 of its value each year and it cost you 20 grand when you bought it. Is this an example of growth or decay? So depreciates, this is going to be decay. And to figure out the decay rate, we take 2/5, let's change it to a decimal, so 0.4. And the decay rate is we'll take 100% of the value and subtract 4% every time, so our decay rate is actually 0.6. What that means is every year, your car is worth 60% of the year before it. So to write the recursive rule, the starting value, so put a sub 0, the starting value when you drive the car off the lot is $20,000. To find the value of the car after any number of years, you take 0.6 of the year before it. So a sub n minus 1 times that 1 minus 0.4, or the 0.6. So it's 60% of the year before it. Find the value of the car after 8 years. Okay, so one way we can do it is we can program our calculator to do this. So I'm just going to pop up Scratchpad here. And so we'll program our calculator by telling it the starting value and hitting enter. And we're multiplying it by 0.6 every time I hit enter. It's the next year. So here's after 1 year, 2, 3, 4, 5, 6, 7, 8. All right, so after 8 years, if it was only 60% of the year before, it's only worth $335 and about 92 cents. So can we write the exponential? So what if you didn't want to program your calculator and hit enter 8 times? What's another way to figure out like an equation for this? And that's the explicit rule. And the explicit rule is you take your starting value and, okay, so our starting value is 20,000. And it's 0.6 to the n power. And so again, for 8 years, what we could have just done instead of programming our calculator and hitting enter 8 times is we can just type in 20,000 times 0.6 to the 8. Let's just make sure that we did it right by checking to see if they're equal. So here's our starting value. Here's our decay rate to the power of 8 years. And you can see that it's the same. So again, in math, you usually have several ways to do a problem. In this case, you do. You can program your calculator and do it recursively, or you can write the explicit rule and do it exponentially. All right, let's take a look then at limits. So questions to think about. Can a person run faster and faster? Can a tree keep growing taller and taller? Or are there limits to these? So here's a tree. Is it growing taller? Does it ever stop? Here's men's marathon record times and women's marathon record times over time. And the question is, I mean, they keep decreasing. Is there a limit? Will it ever stop or will it keep decreasing? Is that possible? And this is hours, right? Marathon is 26.2 miles. And you can see that you can run it like 2 hours. That's crazy. Okay. So let's take a look at the first example. A bowl of soup is 101 degrees Fahrenheit. Zaid measured the soup's temperature each minute for 5 minutes and came up with a recursive sequence to represent the rate of the cooling soup. We can see the initial value, 101 degrees. And the recursion, what it means is each minute the soup loses 20% of its temperature, but then we're adding 15 degrees to that. So the question, is this arithmetic, geometric? And actually this is neither, because it has multiplying and adding together. So there's a name for this. It's called a shifted geometric. So it is geometric because of the 0.8, but then it's shifted. The plus 15 does shift it. So using your calculator, can you determine the value of the soup after 9 minutes? So we can program this into our calculator. Again, when you program it in, you press an 101, hit enter. And then this is like using your last answer key. So if we type that in, here's what it looks like. Okay, so I'm going to clear this by hitting dock and then B. And then we'll type in 101 degrees, tell our calculator that's the starting value. And we're going to multiply it by 0.8 and then add 15. So here's the program. Whoops, I put times 15. We'll put plus 15. Every time I hit enter, it takes the previous answer, multiplies it by 0.8, and adds 15. And the question was, determine the temperature of the soup after 9 minutes. So this is the starting value. So after we hit enter, it's 1 minute. 2, 3, 4, 5, 6, 7, 8, 9. All right, so after 9 minutes, I'm getting a temperature of about 78.5 degrees. Let's just double check and make sure I counted that right. Can I go up? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we're going to write a sub 9 equals about 78.4897. I'll round that to about 5. So I'm writing that right here. About 78.5 degrees. So then it says, what happens if you keep hitting enter on your calculator? All right. Let's hit enter and see what happens. Okay, it's still going down. Oh, but if you notice, it stopped at 75. Okay, so right here, what happens if you keep hitting enter on your calculator? It stops at 75 degrees. Why do you think this happens? Well, it must be room temperature, right? Because unless you put in something cooler into the soup, it's not going to go lower than room temperature. Okay, next example of a shifted geometric sequence. Abdul and Daniel are working at an outdoor pool for the summer. They need to add chlorine to prevent the growth of algae. The first day they add 450 grams, and then they add 45 grams each day after the initial treatment. Each day the sun burns off 15% of the chlorine. Can you write the recursive formula rule that represents this situation? So again, starting value of the chlorine, I'll use A sub 0 because it's what they're adding at first, 450 grams. For any day, the amount of the chlorine is, so if 15% burns off, we subtract that. So it'll be 85% of the day before, and then they're adding in 45 grams. So again, if we're going to program this into our calculator, because we don't know the explicit rule for this, it'll be 85% of the day before, because 15% burns off plus 45. Let's type this in and use it to calculate after 1, 2, and 3 days. Okay. So we're going to clear this doc B to clear it 450 and then enter times it's 85% of the day before, but then we're adding in 45 grams of chlorine. So every time I hit enter, it takes the day before and plugs it back in. So here's after 1 day, 2 days, and 3 days, there's about 392 grams left. So I'll write that down. Okay, oh, where did my thing go? Oh, did I get rid of it? Yes, I did. Okay, hold on. Let me pop back up my screen. Okay, I'll take a second to pop back up. So I'll write that down, and then the next, so I just filled that in for after 1 day, 2 days, 3 days, just by programming into our calculator and hitting enter. So then using your calculator, can you find the amount of chlorine in the pool in the long run? Okay, so in the long run means, does it level off? So I'll hit enter, and let's see, does it level off anywhere? Does it stop at any number here? And you can see that it does look like it's starting to slow down here. So it does level off at 300. Okay, so in the long run just means keep hitting enter. And it does level off at 300 grams of chlorine. And here's, if you actually like graph it, here's what it looks like, and you can see the level off right here. And that leveling off point is called an asymptote. It's like an invisible boundary line, and that equation is at 300 where it levels off. But we won't worry about asymptotes right now. All right, let's do one more example, and then I can show you a shortcut to this as well. SLP Nursery owns 65 pine trees. Every year the nursery plans to sell 20% of its trees and plant 5 new ones. Okay, so the recursive rule, again, I'll start at A sub 0 because we're just starting with that amount. It's not like after the first year. A sub 1 will be after the first year. To find the number of trees after any year, you take the year before it. And if we're selling off 20%, what percent still remains? And that would be 80%. So you have 80% of the trees the year before, but we're planting 5 new ones. So one way that we can do this to figure out, like, is there a limit, is we can program it into our calculator. So one more time, if I hit doc B to clear it, and then this time I'll tell my calculator 65 is the starting value. We take 85% of the year, or 80% of the year before, and we're going to add 5. And we see that the amount of trees is going down, but does it ever stop? Does it reach a limit? And it's starting to slow down at 25, so I'm going to guess it's 25. And we can see that the limit here will be 25 trees. After several years, there's going to be a constant 25 trees if that pattern continued. So in the long run just means keep hitting enter many times. But there's another way to do this. You can actually solve this algebraically. And so what we're looking for if we're solving it algebraically is we're trying to figure out, is there any year that has the same amount of trees as the year before it? So I'm just going to change these to x's and make an equation. So one way to rewrite this is 1x, right? X equals, and this is 0.8x. So I'm just rearranging the letters here. And we're solving for x. So we want to get x on one side. So if we solve it algebraically, this is 1 minus 0.8. It's like $1 minus 80 cents, and that'll be like 0.2 or 20 cents. And then to get rid of the 0.2, it's being multiplied, we'll divide it. And when you do that, you can actually get the limit when 1 year equals the year before it by setting them equal to x, and we can see that either way we get 25 trees in the long run. So whichever way you prefer, if you like solving it algebraically or typing it into your calculator and hitting enter, in a shifted geometric you will have a limit, it will level off. So your assignment then is to complete the next 2 pages in the packet, which are 32 and 33, and then we'll go over any questions in class tomorrow.